This video is about what to look for in a good quality disc. The metal oxide disc is the heart of the MOV arrestor, so it stands to reason that this component is extremely important to the quality of an arrestor. In this video, we will discuss the many aspects of a disc that are so important to its quality, such as the initial design, the raw materials, the ceramic process, and the routine test. These are the critical aspects that differentiate a quality disc from the rest. There are three major materials used to produce a metal oxide varistor. Zinc oxide makes up more than 90% of a disc, with bismuth oxide and antimony oxide being the next two major ingredients. Some of the minor ingredients, also referred to as dopants, are tin oxide, aluminum nitrate, cobalt oxide, nickel oxide, and sometimes silver nitrate. The source of these materials and control of the quality of these materials is paramount to the end quality of a disc. Keeping impurities at a minimum is a major task and is critical to disc quality. Each of the raw materials has a specification which states the limits of impurities. On this typical zinc oxide specification sheet, it shows that the maximum iron content is less than 10 ppm or parts per million. Too much of this impurity can cause the clamping voltage of a disc to be higher than desired, which in turn will result in less protection. Not only are impurities important in a good quality disc, but particle size is just as crucial. This SEM micrograph shows just how complicated particle shapes can be. If the size, surface area, and other characteristics are not monitored and specified, the probability of a good quality disc is greatly reduced. The disc process is generally proprietary in nature, and for good reason. Its development was expensive and took years to refine. Disc quality is highly dependent upon this ceramic process, so users interested in this level of understanding are encouraged to visit the supplier for a first-hand explanation and demonstration. Once a disc is sintered, it takes the shape of a disc we see in arrestors. Shown here is a typical distribution disc. Station class discs are much larger. On the outside surface of a disc is a layer we call the collar. It serves as an insulator and is necessary during high current surges. On the end surfaces are metal electrodes, generally a form of aluminum metal. The top and bottom must be flat and even to ensure good contact between the discs and the arrestor. All three of these aspects are of critical importance and are well controlled to ensure the quality of the disc. If we were to look inside the disc, we would find a very dense green tinted material. It is the control of this microstructure that is of primary importance to a good quality disc. If an SEM micrograph is viewed, we can see the complex internal microstructure in great detail. One of the most important quality checks of a disc is their high current withstand capability. Yes, I know it is done during the design tests, but it is imperative that it be done periodically on production samples also. This test can predict the performance of an arrestor when subjected to its most onerous duty, high current lightning. For this quality test, the disc is impulsed 1 or 2 times at a very high current. The time between impulses can be a few seconds to as much as a few minutes, depending on the manufacturer. During these 2 impulses, the temperature of the disc increases to well over 200 degrees C. Immediately following the impulses, a 60 Hz voltage is usually applied at a level near the disc's MCOV. How the disc responds to the impulses and AC voltage is critical. If it cools and then starts to increase in temperature, we know the disc is damaged internally. If the temperature of the disc continues to drop during the brief AC application, then the disc has passed this test. The final step in this quality assurance test is a physical exam. What we don't want to see are chips or cracks in a disc. Another critical test conducted on good quality disc is one to validate the published TOV curve of the arrestor to which it will be installed. This test is not required by standards, but is certainly used by quality disc suppliers. The leakage current of an arrestor is quite low at normal operating temperatures. However, if the temperature of the disc increases from an operation, the leakage current will also increase. It is shown as the blue dot on this graph. On this second graphic, we can see how the temperature increases after a surge or TOV event. In some cases, its temperature will rise to near the maximum stability limit of the unit. This is how the arrestor power frequency over voltage capability curve, or TOV curve as it is better known, is determined. Energy is injected into an arrestor and then it is checked to see if it will remain stable. If the thermal coefficient of a disk is not the same as it was during the design tests, the temperature of the disk could be pushed into an unstable mode of operation. If this happens, the disk continues to increase in temperature even after the transient event has ended. A thermal runaway occurs and the arrestor fails. Testing the thermal stability of a disk before they are installed in an arrestor guarantees the arrestor's thermal performance in the field. Good quality disk suppliers will have a variation of this test run periodically to ensure TOV performance. A good quality disk always comes with thorough characterization. This characterization comes with a measurement of its impulse characteristic and its low voltage characteristic. This is a characterization of every disk manufactured and is necessary to guarantee the characteristics of a good quality arrestor. The first step in this characterization is an AC or DC test that measures the turn-on point of a disk. This turn-on characteristic is referred to as its V1MA or its reference voltage. Either test works quite well. The second step of its routine characterization is to measure its leakage current. Monitoring the leakage current at or near its operating voltage guarantees the arrestor will not exceed its published watts loss. The third step is an impulse at a current between 0.2 and 2 times the nominal current of the disk. This is a crucial test. From this test, a good quality supplier can guarantee their published discharge voltages. Once the AC and impulse tests are completed, the disk can be categorized and labeled. This information is necessary for arrestor assembly. If the characteristics are not within the max or min limits of the disk, they are pulled from the inventory and not used. The data can also be used to assist in the fabrication process control. If a characteristic is running near its limit, many options in process adjustment are available to the good quality supplier. From the beginning to the end of fabrication and testing of a disk, it is handled with care, but occasionally it is damaged. Physical chips and cracks are not permissible in a quality disk. The very last step in any good quality disk process is a physical examination. This can be done by a person or a computer, but in all cases it is a must. As I stated at the start of this video, a quality arrestor can only start with a good quality disk. Since you will find little public data on this subject, I encourage you to visit a good quality arrestor supplier to see how they do it. As always, we encourage you to stay informed and keep on learning.